Hi guys, I'm substituting for Professor Komarova today. So I'm Alexander Vandenberg-Rodes, and I'm going to teach you integration by parts. So this is section 7.1. I want to start out at the very beginning of the class. Probably the very first thing you learned was the notion of an antiderivative. Was I write G is the antiderivative of little g if this has derivative always equal to little g of x. So this holds for all x. Okay? So the way we figured out how to compute antiderivatives, which is what we need to compute integrals and so forth, is, well, how do we find antiderivatives? The way was we understand how to compute derivatives. So you have, say, cosine x on the left-hand side, and you differentiate it, you get minus sine of x. And I'd tell you that, OK, now we know the integral of minus sine of x is cosine of x. Right? We always figure out integrals by reversing the process of differentiation. So we could do easy integrals this way, compute easy antiderivatives. And now we're trying to figure out more complicated derivatives, which allow us to then compute more complicated integrals. So complicated derivatives. And one way we figured out how to compute more complicated derivatives was through the product rule, which let me just remind you here what that was. So if we have two functions, say u and v, we can take the product and ask what the derivative of that product is. And from Math 2a, you should remember quite well, this was usually written as the derivative of u times what v was plus u times the derivative of v. Okay? And once we have that, we can, of course, undo this process by taking the antiderivative. I'll do that right here. So let's same things like integrate both sides. And what we have over here, so if you undo this operation of differentiation, which you've already done, the antiderivative is obvious. It's just u times v. And OK, on the right-hand side, I'll just write the antiderivative of u prime v plus the antiderivative of u times v prime. OK? Now, this is the starting point for integration by parts. What we do is we're just going to solve for one of these antiderivatives. So I'm going to solve for just this one on the left here. We could choose the one on the right if you wanted to. And let me just write what happens when I solve for this. So if I now say u and v depended on the variable x, we would get integral of u of x times v prime of x dx equals, well, let's write this first. We're going to have u of x times v of x. And then we're going to subtract off this quantity here, the antiderivative of u prime times v. So u prime of x, v of x dx. OK, and this is known as the integration by parts formula. So it's just really you were undoing the product rule. That is the idea of integration by parts. So before I give an example, let me just remind you of differential notation, which is just a more compact way of writing this. And the idea of differentials was we actually defined for functions u and v, the differential of u was just u prime times the differential of x, and dv was the derivative of v times the differential dx. And with this now short notation, we can rewrite this formula in a much more compact way as integral of u dv is u times v minus integral of v du. And so this is a much easier way of writing and also remembering the idea of integration by parts. So let me give a first example. This is a prototypical example. It would be compute an integral like x e to the x dx. Okay. So to understand this formula here, what we're going to do usually is when we look at the top one, because everything's spelled out there, is we have some integral like this one here, and we want to first assign what u and v prime are. Okay, and once we have that assignment, we're now going to see what does the rest of the formula tell us. So what we need, first of all, is to try a 1 u and v prime when we write that as dv. Okay, so we need to try a u and dv. And once we've chosen such a u and dv, we're then going to need to know what v is, and also the integral of u prime and times v, otherwise written as v du. Okay, so we need v, which is integral of dv. And then we also need the integral of v du. Okay, this is like the general method for using integration by parts. So in this example here, for one, let's try just completely random. There seem to be two real functions here multiplied together. Let's try u is x. And dv, which remember what this is v prime of x times dx. I'm going to let this be the remainder of the integrand. That will be e to the x times dx. Okay, so this is our first choice. And once we have this choice, we're now going to try and compute all the quantities on the right-hand side of the formula. So in particular, we would integrate dv, and that would give us integral of e to the x dx, and that's just, of course, e to the x, and plus some constant. Right? And let me just note here that I'm going to put in parentheses here this plus c, because no matter what constant you choose, remember the whole family of different antiderivatives, no matter what constant you choose, in this formula, it'll get subtracted out. You'll have, for instance, if you add a constant to v, you'll get a constant times u minus that same constant times the integral of u prime, right? So they'll cancel each other out. So usually we'll just choose always in the second step, let's let c be 0. And we can not have to worry about writing plus c. Okay, and then once we have v, or this is v was this integral, and then the third step was computing the latter integral, which was integral v du, which using what we have so far, v was e to the x. And du, well, we need to compute that, but that's very easy. The du is just a derivative of x, which is 1 times dx. So this is just dx. Okay. And this is luckily an easy integral to compute. This is nothing other than e to the x, again, plus some constant. OK. So can you, in the back, see below this line? You can see? So I can write? No, you can't see. OK, so let me not write one more line there. Let me instead. Oh, I can just write up here instead. So what we've computed, we now apply the integration by parts formula and realize, OK, this integral here is now easily represented as u times v. So that's x times, here's my v, x e to the x. And then I subtract off the integral I computed here, integral of v du, which was e to the x plus c. And that's it. OK, well, almost it. Let me just make one small remark. Adding the constants at the, you can do it in the beginning or in the end. It's really not going to matter too much. You can write this as x e to the x, just a small simplification here, minus e to the x. And I'm going to write plus c. It should be minus c, right? But remember, the c is arbitrary. You can pick any constant you want. For instance, if the constant was 2, that's fine. That's one possible antiderivative. But if c was 2 over here, that would mean the c over here was minus 2, which is again a constant. Right? So plus or minus the constants, it really is not going to matter. So usually what you can do with integration by parts is just do this anti-differentiation, then add the constant at the end, and that will be fine in this case. Is there any questions so far? No. OK, so that's the case. This is kind of like the base case, the easiest case with integration by parts. So let's try a different. So this will be my example 2. Let's integrate x squared times e to the x dx. Let's try and figure this one out. OK, so let's use the same idea as before. We have two functions here. This one was the function y is x, and this is the function e to the x. So let's do the same thing over here. But now let's let u be x squared. And let's let e to the x dx be dv. So let's try this right now. OK, so let's go ahead and let's figure out this second and third steps. So the second step would be to figure out what v is, which is the integral of dv, which is, again, a very simple integral. It's exactly the one we did before. And yes, I wrote a plus constant here. And again, I'm going to say you can omit this. This is not going to matter. And let's also compute du. That's 2x dx. OK. And once we have that, we now have everything we need. So finally, let's compute integral of v du, which is integral of, well, in this case, v was e to the x, and du is 2x dx. OK. And so if you started with this guy here, you might be stuck. Because, oh, wait, I don't know how to do this integral. Except, I actually already did it. It's computed right here for you. This is my first example. Let me call this actually example 1. Where we compute this integral, and I can use this result from before. And now I have the answer for this integral here. It's just twice what I had before. Right? This is x dx, and that's twice x e to the x minus plus a constant. OK, so now I have, again, all the pieces I need to write out this integral here. So here's v times u is just x squared e to the x, and then plus, minus the integral v to u, which here is twice this whole quantity here, 2 x e to the x minus e to the x plus a constant. OK. And again, you can simplify this if you want. Let me just show you again the effect on the constant. If you simplify, that would be x squared e to the x minus 2x e to the x plus twice e to the x. And now you have minus, don't write this yet, minus 2 times a constant. But you can choose any constant here. Whatever constant you choose, you could divide by minus 2, and it's still a constant. So just to keep notation consistent, we'll just say plus a constant. It doesn't matter. Again, it doesn't matter which constant you've chosen. OK. So one moral here is that if you, for instance, started with this example, or you're given an integral such as this one, and you did the first integration by parts, and you got to well, you got to computing this integral v du, and you're like, oh, wait, I don't know how to do this. Well, the moral is, well, don't stop there. This is something you already can see. This power of x dropped by 1 when I got to this integral. And if you applied integration by parts again, which is exactly what we did in example 1, then you can actually finally solve the integral. You do the integration by parts, and it gives you this as the answer, and then you're done. You've actually computed that integral. You just have to unravel everything. OK, this is what that integral was, and now I can put it together and get the answer. OK, so is this clear? Yeah. OK, so this idea can be used. We can not just do 2 powers of x. We could do many powers of x. So let me just give you a quick example of what it means. The same idea of applying integration by parts multiple times, you can do the following integral. You could, for instance, do x to the 100 times e to the x dx. Some of you might look at that and be a bit afraid. I mean, 100 powers of x. Let's see. So I do integration by parts. What's going to happen? You know, let's just do the same idea as before. Let's pick this to be u. Let's pick this to be dv. OK, so great. What's going to happen? You're going to have u times v, whatever that is, minus integral of v du. And what you're going to get there'll be a factor of 100 from taking the derivative of x to the 100. And then you'll have x to the 99 times e to the x. That's one integration by parts. And I omitted this stuff in here. OK, so here's the game. So we've taken 1 power of x down. We pass it around. And then there's still 99 powers of x left, or beers on the wall, as the old refrain goes. And then we do it again. Now you have 98 powers of x, and you keep iterating the process over and over. So again, integrate by parts. Now you have a lot of stuff. And then you have 100 times 99 times integral x to 98 e to the x dx. And you can keep going. And eventually, you'll get down to an integral we actually found, which is something like this. Just have to do it 98 more times. So in principle, you can do this. Or if you're actually quite smart, you would have a computer do it. Do it the 100 times for you. OK. So this is a method that really bears repeating. There's actually, you can give formulas for integrals like this. This is called, actually, I already forgot the name for it, like recursion formulas. OK. Well, let me ignore this instead. OK. So this is completely clear. You're all happy with it. All right. So why can't we be smart and do something like this for the first problem? Well, actually, not even the first problem. Let's go back to this annoying one. And we could choose different functions, f and g, or u and v, as I put it. For instance, we could let this quantity, let me rewrite this. Let's switch the order. E to the x times x to the 100. Why don't we try this being dv and this be u? Maybe this can solve it for us. Sorry? It goes up a power. Yeah, exactly. So if you do this exact substitution, choice of integration by parts, then v would be integral of x to the 100 dx, which is 1 over 101 x to the 101 plus some constant, but let's let that constant be 0. And du is e to the x dx. So if you do this integration by parts, you're left with some junk to begin it. Well, actually, you can write it out. So the junk is 1 over 101 x to the 101 times, and u is e to the x. Then minus integral of, v is 1 over 101 x to 101 e to the x dx. And this is even worse than before. right? Because now we just increase the power of x, and if you keep iterating the integration by parts, soon you have x to the power almost infinity, right? So the moral here is that integration by parts does not always work. So really this first step of trying here is really a source of the multiple options, and not all of them will give you the way you want to go. So if, for instance, you end up with something like this, like it's even worse, then back up, maybe try again, or maybe you need to do something else, maybe a substitution, or so forth. Okay. You want to do something by yourself? Yeah? Great. OK, cool. So this is the best way, I think, to learn. You're going to do this. Compute this integral. So I'll give you a couple minutes. How many of you have an answer so far? About half the class, even more. Great. So let me just quickly remind you. So the choice, again, should be the obvious one in this case, where let's remove this power of x. So let this be u, and then the sine x dx we'll call dv. And then once you have that, we want to compute v and du. And this is, again, almost routine. This is integral of sine x, which is simply minus cosine. We just write that here is the integral of sine x dx, which is minus cosine of x. And du is simply the derivative of x with respect to x. It's just dx. OK. And then the last thing was this integral here, which is integral of v being minus cosine x. And then du is dx. And this is the integral we can do. Right? This integration of minus cosine x, and that's minus sine of x plus a constant. And now you have the actual formula. So u times v is simply x times minus cosine x minus this integral we computed here, which was minus sine x plus a constant. Okay. I hope that's what most of you got. Okay, so unfortunately this method, it's great. We can do many integrals with it. But this application, like always reducing powers of x by choosing, for instance, like this x, the first power, as being our choice of u, doesn't always work. So here's the big but. Suppose you had an integral like this, x to the fifth natural log x. Okay, why did I write but here? Well, let's use integration by parts, but with the standard choice. U is x to the fifth, dv is natural log x dx. And then if we compute in step 2 what v is, it's okay, it's natural log, integral of natural log of x dx, which is, well, I don't actually know what it is. Well, okay, I know what it is, I think. Some of you may not know what this is, and you'd be stuck at this point, because you can't proceed any farther. You don't know what a closed form expression for v. So already we're stuck with this choice. And let's try something else. Question? No. Not a question. So if we're stuck here, then let's try again. Let's use a different choice. Let's try the other way around. You could, for instance, try u to be the natural log of x and dv to be the remainder, x to the fifth dx. Okay. So in this case, what's going to happen is we're going to increase our power of x here when we calculate v. So in particular, in step 2, v is this integral of x to the fifth dx. And you might remember, this is quite simple integral. You just add 1 to the power of x and divide by the power. So it's x to the 6 over 6. I'll choose a constant to be 0. And du is now the derivative of natural log of x times the differential dx. Right? So this is where the magic comes in, is that, well, natural log has a really nice derivative. It's just 1 over x. Yeah, you already can anticipate where this is going. Now with this magically nice derivative, we can see that the third step is now incredibly easy. In fact, some of you can have already done it in your head. So if you integrate v du, what you're left with is integrating x to the 6 over 6 times dx over x. And lo and behold, the negative 1 power of x here cancels with one of the 6 powers of x up there. And you're left with the integral you can do. This is, we've pulled the 1/6 outside, and you're integrating x to the fifth. And this is now routine. You just get 2 factors of 1/6, and you have x to the 6. Oh, wait. I'll write plus c here. OK, and that's the answer to the third part. And now the complete integral is very easy. We can just write it up here. If I go back, we have u times v. That's just x to the fifth, and v. U is natural log x. And then we have v is 1 over 6 x to the 6. And then we subtract away from that the result. We have that integral over there, which is 1 over 36 x to the 6 plus a constant. OK? And that's the entire answer. OK, so there's a clear moral to this story, is that choose sometimes u to be function with nice derivative. In this case, natural log had a very nice derivative. We can very easily differentiate it. When we do so, it made the resulting integral very easy. OK. OK. So no questions so far. It's all quite clear. OK, so we have the following. I want to illustrate this moral here with arctan x dx. And this is exactly the type of situation where this moral applies. Just write this as a note, is that the derivative of arctan x is 1 over 1 plus x squared, which is quite a nice derivative. It may not seem like an amazingly nice one, but it's clean. You actually can understand it pretty well. Arctan, the inverse of the tangent function, is not immediately obvious what it is. OK, but its derivative is nice, as we know. So let's use that. So that the idea here is like try, or this moral, try u to be arctan x with integration by parts. Because initially you look at this integral and say, I don't see two functions to choose for my integration by parts. I only see one function. I only see arctan. Right? Well, where's my second one? It's just the 1 dx. Yeah, like there you go. So let's let this be u, this be dv, and the result is quite nice. So we used the second step is v is integral of dx, which is nothing else than x. And u, du, we already wrote over there, that was dx over 1 plus x squared. OK, and now with that, we can complete the almost complete the integral. So in particular, for the third step, if we want to compute integral of v du, that's the integral of x times dx over, let's put everything over it, 1 plus x squared. OK. And, oh, we're actually not done yet. How do we do this integral? Are we stuck? Sorry? Yeah, I hear integration by parts and substitution. And now, yeah, more people see substitutions because we recognize this function on the denominator, 1 plus x squared as derivative x, or it's like 2x. And it's very close to what we have here. So if you now use another method, substitution, try u is 1 plus x squared. Now note, this is a different u than we used with integration by parts. I'm now only tackling this integral here. And so we have du is 2x dx with the substitution method. And on top, we see exactly 1/2 of du. And on the bottom, we have a u. So this is now a simple integral to compute with the substitution. This is integral of 1/2 du over u. That's a substitution. OK, if you're a bit confused by this, notice all I did is I substituted 4x dx by dividing this by 2. OK, and now we can compute this integral. This is no more than 1/2 natural log absolute value u plus a constant. And now we can substitute in for u, recall what it is. We want to get back to original variable x. And that's 1 plus x squared. That's the constant. OK. So here's the final result. I can compute this final integral. And now we have, see if I can write it right here. We had u times v, which in this case, oh, I should not have erased that. Oh, that's too bad. I think we remember quite clearly this was u, and this was dv was dx. So in particular, v was x. OK, so u times v was x arctan x. And then we subtract off this integral that we computed here. This was v du, and we got the result 1/2 natural log 1 plus x squared plus c. And there's one last simplification you can do. Maybe this is already obvious to you. I'll place the absolute values by parentheses precisely because x squared is always positive. I'm adding 1 to it. So taking the absolute value is not changing anything here. OK. So that's a nice result. So this is a very general method. You can do this for many cases where you have just one function you're trying to integrate. You can choose that function to be the u, and then when you do the integration by parts, you'll get the derivative of that function times an x, just like we had here. 1 over x squared, and then times an x, and that we could integrate. OK. That's it. Any questions? I keep asking you like every 30 seconds. So please do say no. OK. All right, so the very last one, integration by parts I want to do is a standard tricky one. This is the last example. E to the x, let's do cosine. Okay. So let me do this maybe slightly faster. So we already have the idea of, OK, we're going to divide this into functions, and it's only really two possibilities, more or less. Then we do kind of the obvious one. Make u be e to the x, dv is cosine x dx. And let me just do the integration by parts right here. I'm going to skip writing down the second and third steps. You already see how to do that. And we see u is e to the x. V will be the antiderivative of cosine x, which is just sine of x. So it's e to the x sine x. And this is my u times v. All right, and then I subtract off from that the integral of v, which is sine. And du was e to the x dx. OK, so this is one integration by parts. I've just left out writing down my v and du. So this is one integrate. OK, so we did it once. And we get this integral here. And it looks surprisingly similar to the integral we started. It's just sine instead of cosine. You still have this e to the x. So let me just rewrite it slightly. I'll just reverse the order. Now it looks even more similar. But it's sine instead of cosine. So here's what I say, have fortitude, don't give up. Integrate by parts again. That's kind of like all we have to go on. There's no obvious substitution or any other technique that you can think of. So let's do this again. So I'm going to compute now. Let's compute the integral of e to the x sine x by parts. And now I'm going to have, again, a different u and v. well, the u, let's make the same. U is e to the x. And then for dv, it's now going to be sine x dx for my dv. And again, we can solve for what v is. V is the antiderivative of sine of x. Let me actually write that down here. This is minus cosine of x. And u is, of course, e to the x. I don't need to write that again. And so we get here is e to the x times minus cosine x, u times v. And then subtract off integral of v, which is minus cosine x, times du. And du is just e to the x. Okay. So that's my second integration by parts that I've done. And let me just rewrite this. I'm just going to simplify, cancel the minus signs over there, and put this minus sign out in front. I get minus e to the x cosine x. And these two minus signs cancel, and I have plus. And let me just switch the order as well. Here's e to the x cosine x dx. And now I want you to take a good, long, hard look at this. Do you see anything?
It's infinite.
It's infinite. How to get infinite?
If you keep doing, it keeps repeating. Now it's going to go to e to the x sine of x, and it's going to go again to the negative cosine of x, e to the x, and go back to sine.
Yeah.
Over and over again.
This is bad, right?
To the other side.
Yeah. So what can we do to get out of this infinite loop? Sorry?
Use cosine
Trying to do substitutions, which also chain rule, same thing. Yeah, but it's not clear. Like u is cosine x. How do you express e to the x in terms of cosine?
change the u and dv.
Oh, so you want to do it by parts again?
Yeah.
Oh, that's what he recommended there. And what you get is this, right? Like, oh, you want to change. So like, I see. So you want this to be dv, and this to be u. We could try that. Well, sure, we could try that very quickly. If you just change this, and so you want this to be dv, and this to be u. When you do it, again, you're going to get a du will be sine x, and this will be e to the x. It's going to come back to the same thing again. Yeah, on the way back.
As the integral of e to the x cosine of x dx on both sides?
Ah, OK, you're doing something tricky. So what he said was, let's write out this entire thing. Let me continue what I wrote in the beginning. It's my first integration by parts. I then computed this. So let me write out the entire quantity minus, all right, so what did we compute? This integral was minus e to the, minus e to the x cosine x. So be very careful of signs, else you could get something completely wrong, or you won't make sense of it. And then integral of e to the x cosine x. Okay, so the idea was if you expand out this bracket, I'm just going to do it right here for you. These two signs will cancel. You're going to be left with a plus, and this will change to a minus. See, right? You have the same integral on the right and on the left. And so let's add that integral to both sides. So and let's go all the way to the left-hand side. We get twice. And look at the magic. Magic is this is 0. This, and there's your answer. Well, there's twice your answer, right? Twice the integral we started with is this quantity here. So let me write this out in a way that's a bit more clear. So what do we do? Let's call this original integral I. This is just defining I to be this integral. And we discovered, just to restate what I did here, we discovered that this integral was this quantity, e to the x sine x plus e to the x cosine x minus I, because it's the same thing, the same integral we started with. And then we just solve this for I by adding I to both sides. So let me just do again what the suggestion was, is we add I to both sides and get I plus I equals e to the x. And I'll put this in parentheses, sine x plus cosine x. Right, just solve for I. And here's the result. I is 1/2 e to the x sine x plus cosine x. And that's the final answer. Any questions? Okay. No? Yeah?
Is this kind of technique unique just to this problem, or can we do like this for?
There are a couple other cases, and the cases occur when you notice e to the x has derivatives and antiderivatives just e to the x, and cosine x has derivatives and antiderivatives in terms of sine, which then goes back to cosine. So only when you have this continual flipping will you get something like this. So you might have, cosine 2x, for instance. You might have to use the same technique. Okay? All right. Thanks, guys.